Okay, so yeah, let us start then. Is my screen visible?
Yes,
Yes.
sir.
Yeah. Okay, so week 9. And let me take the questions in sets of 5 or sets of 3 maybe. So I'm going to take the question number 5 and 6 in 9.2. And any other question from any one of you? Can be
Venkatesh,
from.
just a suggestion. I mean, not that I would want you to do it this way, but if we proceed from the beginning and we just list down all the doubts, it helps us to clarify any doubts from the previous weeks also, and then it builds on to the uh, higher weeks doubts also. So if that approach is follows listing down all the questions, we'll also be clarify what is coming ahead, and then you might want to just keep adding for the preceding weeks. When we go from week 9 to week 5, then it
Mhm.
becomes like a jump to the previous things where the doubt are already from the previous weeks.
So you
However, I
want me
leave
to
it up to
do.
you to
No, no,
take
you
it
want me
forward
to
the way.
do from week 8, week 9, like that, or
I mean, whatever weeks, the first weeks that we have the doubts from,
doubts?
we
Okay.
can take that particular week as the starting point, and then perhaps gradually week
Mhm.
towards the later
Towards the
weeks.
week 9, yeah,
Yes,
understand.
right,
But
right.
what if we spend more time on week 7 and 8 doubts, and if you are running out of time? Okay, okay, let's decide on the number of doubts students has. Okay, if there
Yeah,
are less
exactly,
doubts,
right,
yeah.
right. And then accordingly, you
Yeah,
might want
Yeah,
to
yeah.
consider. Sure.
So yeah, you can post your questions now. I guess you can ask one by one, and let's see.
I have doubts from week 7,
Hmm.
practice assignment,
Okay.
sir.
question 6, question 10, 8, and 11.
Oh.
So question 6 and question 10 are interrelated,
Hmm.
and 8 and 11 are separate.
Okay.
And basically, it is not exactly the question, but some doubts around the beta distribution from question 8. And from question number 11, I wanted to just understand the normalization process in a better way.
Okay.
Yes, right. Thank you.
Okay. Anyone? See, I can see 56 people. So you might have come to this session to learn something, or maybe you might have some more doubts with you. So I heard many comments that students are facing many problems in stats too. So problem can occur either you are unable to understand the concept, or
Sir,
yeah.
sir, 9.3, first question.
Okay.
Sir, as Apple said his was correct, but the session was on week 9. No, week 9, no, sir. First, we can finish week 9 questions. Later on, we can focus on this previous
Okay,
weeks.
okay, yeah, yeah. See,
Mm,
that will depend on how many number of
the
questions I get now. So if there
Yeah,
are
yeah. Oh,
only this number of questions, I can complete every question within 2 hours.
mm,
Okay.
okay, sir.
Yeah. Okay. Then
Sir, I have
yeah.
sir, I have a doubt in lecture 9.5. Capture recapture problem.
Okay. Lecture 9.5. First problem, I suppose.
Yes, sir. Uh, in this problems, I think expectation value of m. I cannot able to understand how they find
Expectation value of.
m. Something m was there.
Okay. 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 Let's see that thing also. Okay. Okay. Let us start then. So let me see what is this practice assignment week 7 questions are related to. If it doesn't relate to these questions, I will complete week 9 and I will move to week 7 then, if there is no interrelation between those two. So if there is an interconnection, then I might start from week 7 questions and I will come to week 9. Is that okay?
Sir, I have one doubt.
Hmm.
In yesterday session, ma'am had something say about T distribution. I cannot able to understand what is T distribution.
That will come in future. Okay, no need to worry in week 9 itself. Okay. Hello.
Okay.
Yeah, z table, z distribution, and t distribution will come later too.
Sir, hello.
Hmm. Yeah, hello.
I have a general doubt in determining the confidence intervals. Sir, my question is, why we are taking every time we are taking like that estimation parameter, suppose it is lambda hat to be the mean of the distribution or the sample. Like every time, why we are taking that?
See, that is the best estimator, right? That turns out to be the best estimator. That mean turns out to be the best way I approach my parameter. So while you're finding using methods of moments estimator, or so there are different kinds of ways, different ways you find the estimator to your distribution. So when you use those ways, like I can use methods of moment estimate, maximum likelihood estimate, or newly in this week 9 we have learned Bayesian estimator. So these all are ways to estimate our parameter for the given distribution. So when you use these methods, we are more or less finding that our best estimator is nothing but the mean of that particular sample.
Okay, sir. Okay.
See, there can be many estimators, as you can see.
So my doubt is every time why you are taking like every time it is mean and we are doing that error to be zero. That I understood error to be zero. But why mean every time?
See,
Okay, sir.
not every time it will be mean. When you consider exponential distribution, when you are trying to find an estimate for your lambda in your exponential distribution, so then it will not be your mean. It will be something like, if I am using methods of moments estimator, then it will be like n by x1 plus x2 plus and so on plus xn, which is different from mean. That particular thing will be the best estimator. Usually our questions are based on binomial, not binomial, Bernoulli, Poisson, and what else? So usual questions are on these distributions. So we tend to get mean value. So lambda hat will tend to be like sample mean. And once you get the lambda hat, why we take the expected value of lambda hat minus lambda is because, see, this is expected lambda hat and we have actual lambda hat. So once you have two things, expected and actual, once you are expecting something and there is some actual thing, we will be interested to know how accurate or how closely we expected uh, with respect to actual value. So what is the difference between my actual value and my expected value is what usually we are interested to check, right? So if I'm expecting something, that should be very close to my actual world. So that is why we consider the difference between the expected estimator value and the actual estimator is. So that's why we subtract those two. We see the difference, which will be the error, and that error is basically a random variable. So once you have one sample, you will get one lambda hat. Once you have another sample, you will get different lambda hat. Lambda hat is an random variable. Now lambda hat minus lambda will be a random variable. Now you have a new random variable, and once every time if you have a random variable, people or everyone is interested to see the mean of that random variable or expected value of that random variable, right? What can I usually expect from that random variable, the output of that random variable. So that is why we take expected value of lambda hat minus lambda.
Okay, sir. Thank you.
Okay. So yeah. So question number 6 is a study shows that the average daily sleeping hours of teenager is 10 hours. Is that the question? Apul? Apul or someone?
No, that was
Yes,
not
sir.
from my end. It was from someone else.
Yeah, I asked for 9.26 is
Practice assignment 7, question number 6.
Oh, okay. Practice assignment 7, question number 6. Yes, that is from my end, right?
A study shows that the average daily sleeping hours of teenagers. Can you
Right,
confirm, is
right,
this the
right.
question,
Yeah,
right?
this is the question. So question 6 and 10, I can just let you know what my doubt is also.
Mm-hmm.
So over here we have taken this FZ um, distribution and then come to the conclusion. So my doubt is, why did we not use the normal inequality where we are calculating basis sigma square upon n delta square when all the parameters are given? Then also, why did we go across and solved using normalizing and then taking it forward?
So how do we know to find the probabilities of the normal distribution when mean is mu and variance is sigma square? How can we find that?
So if we put the formula sigma square upon n delta square,
Hmm.
then we can reach to some number which will give us the higher bound,
Hmm.
right?
Hmm. That is
And
the bound, right? You are using Chebyshev inequality, I suppose, right?
yes, right.
So you are using these inequalities will give us bounds, not the exact value of probability. Here the question is, what will be the probability that the mean of the sleeping hours of these 100 teenagers is at least 0.4 hours? So we are actually asking you the exact probability value.
No, so when it says is at least 0.4 hours away from the population mean. So the
Hmm.
question is, what will be the probability that the mean of the, okay, the probability. So fine. Would then my question becomes, would doing that particular thing sigma square upon n delta square is also right?
See, that is actually, it will actually give you an upper bound to your probability. So what if your probability value, see this, maybe let's say option A is correct in this. I don't know the answer.
Hmm.
If your option A is correct, this has some value, right? 1 plus fz of minus
Yes,
2
this will
minus
have some
fz.
value,
This
right?
is a particular value. So
Right.
let this be something like 0.05.
Okay.
But when you use that sigma square upon n sigma n delta square,
Yes, that will not give the value. You are right.
that will give
Okay.
you something like 0.25 or 0.30,
Okay.
whatever you
Okay.
calculate.
Okay.
See, your probability, that assures you that your probability that the mean of the sleeping hours of this 100 teenagers is at least 0. Hours away from your population mean is actually less than or equal to 0.3.
Okay.
That is only you will get.
Okay.
You will not get the actual probability value.
Hmm, hmm, hmm,
In
hmm.
order to get the actual probability value, we will standardize these things because we know the exact probability values for standard normal.
Right, right.
So using the tables, okay.
Okay.
So
So
yeah, I
that
hope
is where whenever we have to calculate the exact probability, we have to resort to something of FZ, taking
FZ.
FZ
Yeah,
to
yeah. You just have to convert uh, any distribution to standard normal distribution.
standard normal distribution. Yeah. Okay.
Okay. So yeah, see, look at the question. If they are asking find the upper bound of the probability, then you can use those Chebyshevs or Chernovs or whatever. So maybe Chernoff you can use for better upper bound.
Yes. No,
Okay.
this makes clear. I mean,
Yeah. So if they
why
are
we are
asking,
not using that normal thing and instead of solving it through the normal, taking the standard normal, this is clear.
okay. So what is question 10 then?
Question 10 is also on the same lines because, as I said in the beginning only, 6
Yeah,
and 10
yeah.
are
See,
interrelated.
here also the same thing. What is the
Yes, right.
probability that the mean weight? So we are asking the exact probability value.
Yes.
Okay. So even this is okay.
Yeah.
So what is question 8 now?
So question 8 is this
Okay, gamma.
gamma, right?
Okay. So what is
And
the
I did not understand the application of the beta distribution in this question.
application of beta?
Yeah, so I have seen the solution. The solution
Mm-hmm.
is available.
Mm-hmm.
Uh, it simply it simply states that x upon x plus y,
Mm-hmm.
and the expectation has been taken as 2 upon 2 plus 5. However, this 2 upon 2 plus 5 is the expectation of the mean value of beta distribution.
Mm-hmm.
Then how that 2 upon 2 plus 5, which is alpha upon alpha plus beta, is the answer to this particular question is my confusion.
Uh, okay. Have you
Why
watched the
x
lecture of
upon,
this?
yes, I watched the lecture.
So we are not worried about how it comes, but we know if you have two different random variables which follow, so one follows gamma,
Gamma,
alpha
right,
1 beta,
right.
and if other random variable follows gamma, alpha 2 beta, okay.
Yes, right.
uh, Now in the lecture also it is said that x by x plus y
Yes.
will follow
Beta, alpha comma beta.
beta, alpha comma beta, alpha 1 comma alpha 2,
Yes, right, right,
okay.
right.
So this is what in lecture also it is given, and also professor stated that you don't need to worry about how this came, but this
Yes,
is an
right.
interesting observation to look at.
Hmm,
Okay, so now we have given you two distribution for values of alpha 1, alpha 2 and beta are given to you. So it said that x follows some 2 comma half and y follows some gamma 5 comma half, right? Now
hmm,
from this you can see alpha 1 is 2, beta is half, alpha 2 is 5, right?
hmm,
And what is the question? Question is about what will be the expected value of x by x plus 1 random variable.
right.
Okay, so we are interested to find the expected value of x by x plus y. So let me call this as z something. Okay, so this ultimately I should find the expected value of z.
Exactly. Correct, right,
Okay,
right.
now z, what will z follow? What is the distribution of z, random variable z?
Beta.
uh, Now z follows, so see alpha 1 is 2 and alpha 2 is 5. So what is alpha 1 comma, so z follows beta, alpha 1 is 2, alpha 2 is 5,
Hmm,
right? Now z follows if your random variable z is beta 2 comma 5 distribution, what is the expected value of z?
hmm.
So you tell me, if I have a beta distribution, what is the expected value of beta distribution?
Yeah, so where I got stuck over here was I know expectation of anything would be fx into its distribution,
Hmm.
fx into, but then w- and this was not what I was able to carry out. How do I write the expectation of z over here? What would be fx and what would be its distribution?
Okay.
Distribution is beta, but then I was not able to go forward from this particular step. And when I saw the solution, it just mentioned 2 upon 2 plus 5. So that is the disconnect
Okay,
which I'm
then
having. I'm
you
not
are
able to understand over
you
here.
are not getting this thing then. So if you have beta, alpha comma beta, so two parameters alpha comma beta,
Hmm.
so you are not getting this expected value. So if the random variable is alpha by alpha plus beta, so how is this true is your question, right?
Yes, correct, right.
So you can get this from the same thing we follow. Write fz of z first.
FZ
So
of Z, okay.
so what is fz of z? So
Uh,
what is
yeah,
the
that would
PDF?
be x raised to power alpha minus 1.
That is so okay. So it is proportional to x raised
Proportional
to
to,
alpha
right.
minus 1 times
1 minus
1
x raised to
minus
power
x
beta
raised to
minus 1,
beta minus
right.
1. Okay. Okay. Uh, See, for this you need exact value of fz. Okay. I will
Yes,
give you.
exactly, right.
I will
Right.
give you the exact value of fz now. So it will be related to gamma. Okay, PDF will be gamma alpha gamma beta by gamma alpha plus beta.
So this is
Okay.
the first part when we are calculating the
Expected
PDF,
value.
right? Right. Expected value.
Yeah.
Yeah.
So see,
Okay.
why we ignore this is we don't know what is gamma function yet, right? We haven't seen what
Right,
is
right,
gamma. So
right.
that is why even professor didn't want to bring these things.
Yeah, okay.
So that is why he said this fz. See, this is nothing to take. This is just a constant.
Yeah,
So
fine.
that is why
Okay.
he said our PDF will be PDF of beta will be proportional to x power alpha times 1 minus x beta minus 1. Now
Right.
what we do is we just have to, if you want the expected value of z, you just have to multiply x to this, right?
Hmm.
Integral wherever support of x, support of z,
Hmm.
support of z. So x times gamma alpha gamma beta by gamma alpha plus beta into x power alpha minus 1 into 1
And we
minus,
consider that to be constant, right? The one
right?
which we have not
Yeah,
read in the lectures, we say that is the constant C.
that is a
Okay.
constant, but it depends on the constant. No, you need to know the function value, gamma properties.
Yeah, okay.
Gamma alpha is alpha times gamma alpha minus 1.
Okay.
So these all are required because we are going to do some manipulations here.
Hmm. Hmm.
We will do some manipulations and we will
Hmm.
get again a beta where it
Okay.
integrates to minus infinity to plus infinity and it becomes 1, and we will be left out with alpha by alpha plus beta something, and
Okay.
this will be
Fine.
minus infinity to plus infinite some other beta distribution.
Okay.
So we will get alpha plus 1 time something like this.
Hmm. And this will eventually
And
evaluate to 1.
this will eventually evaluate to 1.
Yeah.
So you no need
Okay.
to worry about the proof. But ultimately what we will get is, if you, even though you use this, if you know this, multiply x. So after
Yeah.
doing all these things, we will ultimately reach to this point. So
Okay.
expected value of z will be alpha by alpha plus beta.
Okay.
Okay.
Fine.
Once
Yeah.
you get this, it is, I guess this is alpha by alpha plus beta. And this will be, you know, alpha, you know, beta. Okay. You don't
Yes.
need to worry about the solid proofs of expectations. So we are not going to ask you to prove something. Okay.
Yeah.
And even though you even also you no need to mug up the things, we will give you. We
Yeah.
will give you the table.
No, so where actually the doubt arose, it's fine. If it is not required to learn the proof, everything, that's okay. But in the lecture also,
Hmm.
expectation of X is not given. The mean has been given, the variance has been given, everything else has been given, but uh, expectation of the distribution is not given to be alpha upon alpha plus beta. The mean has been given upon alpha plus beta. So am I
Okay.
missing something over here?
Mean is expectation, right? Mean is first moment.
Yeah, mean is first moment, right?
First moment is expectation of
Expectation.
x,
Hmm.
right?
Okay. Yes, right, right, right.
So see, mean
Yeah,
actually is the expected value. So both are same. Mean, expected value, both are same.
got it,
Okay.
Venkatesh. Clear,
Yeah.
right, right.
Okay.
Fine.
Okay. So that is regarding this. And okay, what is the last question? Question number.
That is around normalization. And I
Okay.
can be specific which step I did not understand. I have the solution again for this.
Hmm.
This was question number 10. Sorry. Um,
Question number 11.
Question number 11, right?
Question number 11, right?
Yeah. And over here, this in order to carry out the normalization, I understand that we divide it by root n upon sigma.
Hmm.
I'm referring to the solution exactly, and I did not understand the last part of the solution. Are you sharing the solution? If
No, I'm not sharing. I'm not seeing. I'm
okay,
just seeing the question. Do you have to
okay.
share the solution? Do you have to open the solution of this?
No, then I can be just specific what I did not understand.
Okay,
Otherwise, you'll have to
just
go through
give
the whole
us.
solution.
Okay, just give me a second. Then.
Yes, please.
Is it okay?
Yes, yes.
Okay. So what is the thing?
How have we approached from fourth arrow to the fifth arrow?
Fourth to fifth, is it?
Yeah, the fourth arrow that you see in the
This
last
thing.
part. Yeah. So from fourth arrow to fifth arrow is what I could not figure out.
Okay, just multiply root n in the inequality throughout the
Multiplication with root n.
hmm?
Multiplication with root n.
Multiply with root n. So you
Mm,
multiply root n to the minus 0.1, you will get minus 0.1 root n.
root n, right?
Okay, you multiply root n here. Now n can be written as root n times root n, right? One root n and another root n will get cancelled, and you will remain with one root n.
But then how that s minus 4n becomes s minus 2n in the numerator?
Okay, that is that should be 4n only. I guess that is a mistake there.
I see.
Okay, that is
Okay.
4. See, that is an error. That is 4n only.
Okay. So this will, I mean, because we are multiplying it with root n, and hence automatically the denominator becomes 2 root n, which is the required
Yeah,
condition for normalization, right?
right. You see here, right? S minus 4n by
Yeah,
2
yeah. I
root
mean, I
n
see this
is
particular thing, and this was the confusion. Why this s minus 4n has become s minus 2n?
no. That was an error from our side. So that should be 4n only.
Okay, Venkatesh. Thank
Okay,
you.
okay, okay. So yeah, let's come back to week 9 then. So we are done with this. So someone has posted in the chat that 9.1 question 1 and question 2. So AQ 9.1 question 1 and question 2. Okay, let us go one by one. So I will start from 9.1, 9.2, 9.3 and I will come to the lecture 9.5. Okay, we will start from here. We'll go here, here and here. Okay. Is he there? Who asked this 9.1 question 1? Can you unmute yourself, please? Or you have to check the chat box again. Hello? Tushar Bharti. Is he there? Okay, do any one of you have doubt in this question 1 and 2? Or else I just skip this question.
No, sir. Actually, that was straightforward.
Yeah, okay. Okay, then let's move to 9.2. So what are the questions? 9.2, question 5 and question 6 is,
Last two.
yeah, last two. Okay, let me see the questions then. Just a second. Okay, so consider 5 IID samples, 2.54, 6.5, 4.5, 3.5 from a normal M comma 1. This is the question, right?
Yes, sir.
Hmm? Okay. And also find the posterior mean of M using normal 10 comma 2 square prior. Okay, so what shall we do now? So it is given that. Okay, let me take my screen back. Okay, we have been given some 5 samples. 5 1 minute. Yeah, 5 samples which are IID normal m comma 1. So this is sigma square. This is right. So also it is given, we have been given you the prior for this one. So you cannot use this. So prior for m is
Sir, one is
normal.
only sigma, right, sir? Not sigma square.
1 is sigma square, right?
Sigma square, sir, or sigma?
Okay,
I
you
think
are
it's always sigma square only, sir.
see whatever the parameter here is represents sigma square. So if I
Square.
say, yeah, normal 4 comma 5. So 4 is the
Yeah,
mean and 5 is the variance, not the standard
variance.
deviation. Okay,
Okay, sir.
mean, and this is variance, which is sigma square. This is mean. Okay, so 1 square is 1. So that is sigma square. So given prior
In
is
fact, in week 5 lectures, it was told
huh?
corrected as sigma instead of sigma square.
Yeah,
Professor has corrected.
Professor has written sigma, is it?
yes, sir.
Yeah, in fact, he was just specifically referring my apologies for confusing. It should be sigma. He was writing, but
No,
the
no, no,
notes
no,
were
no.
written as sigma square.
He apologized for considering it as sigma.
Oh,
Huh?
Just go back
What
to
is
the
it?
lecture and see. So he was using this particular 5 as sigma, and he used it, and he said usually we refer normal mu comma sigma square. So that is the usual denotion.
Actually,
That's
sir,
the usual one, but
Yeah, in lectures, professor used this thing as sigma, and he apologized saying that I use this as sigma, but follow the usual trend. Don't be confused.
there
okay,
was
sir.
no
no.
example in the video, right? Like when the lecture was going on, did he refer to any examples? I don't see any examples in the 9.2 video. I don't
9.2
see like
video.
no. I mean
Exam.
9.2 lecture session. Sir did not give an example for this. He only gave the formula kind of how we arrive at. He didn't say any numbers, so I don't think. I think he's telling about the next video lecture or something. I saw only till 2. There was
Okay,
no.
okay. This is not regarding. This is when this came in 9.3. Is it for
Yeah,
any estimators? Yeah.
I didn't see that 3, but in 9.2 he didn't discuss anything. And but before this, when he told about the normal distribution, he said it's always the variance and not the standard deviation. The usual way of writing normal distributions.
Right. See, this is the usual denotation. Mu comma sigma square are the two parameters. Mu is mean and sigma square is variance. And this is the general denotation of normal distribution. But professor in
Okay.
between he used the other parameter as sigma for calculation purpose, and he used it and he apologized for that. Just watch the lecture again and you will get the clarity.
Okay. Thank you, sir.
Yeah. So prior is given to us as something 10 comma 2 square. See, okay, 2 square. Now here 2 square is variance. 2 is the standard deviation. Okay, yeah. So let's write what is FM, PDF of FM. What will be the PDF? 1 by root 2 pi sigma naught. Okay, this is sigma naught square, and this is mu naught. So you write the values down. Mu naught is 10, sigma naught is 2. So now the distribution PDF of this prior is 1 by root 2 pi sigma naught. Sigma naught is 2 into e to the power minus mu naught. Mu naught is 10 whole square divided by 2 sigma square, sigma naught square, sorry. 2 sigma naught square is 2 square. So this will be the PDF of the prior, right? PDF of normal 10 comma 2 square. Okay. Now, what is the question? Question is about find the posterior mean of m using normal 10 comma 2 square. Right? What is the posterior? What will be the posterior?
The lengthy formula, I was little scared.
Okay, posterior will be likelihood times prior, right? Also, if you find the likelihood, what will be the likelihood here?
Every item minus the mu, right? So, the whole square, addition of all
Right,
this
right,
power to the exponential.
right. So now likelihood, I will say L is given to be pi equals to 1 to, so pi is the product of all the 5 probabilities. So pi times pi 5, so it will be 1 by root 2 pi sigma naught. Sigma square is 1 anyway, so it will be e power minus xi minus m,
Square.
right? xi
The
minus
whole,
m, xi minus m or xi
all
minus mu,
squares, mu the whole squares.
yeah, mu whole square by 2. 2 sigma square is 1 anyway. So this is the product we wanted to find. So as this is a constant, we don't need to worry about the constant part in this. We can ignore this constant part. So once you ignore that, we will left out with e power minus half times of x1 minus mu whole square plus x2 minus mu whole square and so on plus x5 minus mu whole square. Okay, so we have likelihood with us, we have prior with us, so we need to find posterior, right? What will be the posterior? Be proportional to, it will be proportional to e power minus half, I will write it as summation I is equals to 1 to 5 xi minus mu whole square times prior.
Right.
So even in this prior also, we no need to worry about the constant part. So it will be e power minus mu minus 10 to the square by 8. So this is what the posterior is. And if you simplify this, you will get e power so in the lecture it is given, right? In the lecture, what is this thing will tend to. So if you have posterior
So in
density
the
like
left,
this,
so
If it tends
what is
to
the
infinity, it says n sigma square divided by n sigma square plus sigma square.
tends to?
When n tends to infinity, the first part, the likelihood part will be sample mean into n sigma square by n sigma square plus, I mean sigma naught square plus sigma square plus the prior mean mu into sigma square divided by sigma. This is
So
what
you are
where I'm
talking about
confused.
posterior mean only, right? Posterior.
Yeah, posterior mean, that's the final formula here. I stopped with that, it was really confusing.
Okay. Posterior mean, I can say mu hat or something.
Yeah, mu hat, correct. Mu hat is
Mu
equal.
hat, yeah, can be written as x bar times, correct me if I'm going wrong, sir. N times sigma naught square by n sigma naught square plus, so this is, So once you have this posterior density, right? This is proportional to this, and you know this follows some normal when n tends to infinity. So you can compute the posterior mean like this. So it is given like x bar times, so where x bar is actually the sample mean. So x bar is x1 plus and so on xn by n. So this is x bar, and that multiplied by n sigma naught square by n sigma naught square plus sigma square plus I guess mu naught times sigma square by n sigma naught square plus sigma square. Is this correct?
Oh, this is correct, sir. But where do we have a sigma naught square and all? We have not computed that. Sigma square.
See,
Sigma
sigma
square is
prior.
yeah.
Mu naught and sigma naught are the prior
Oh,
mean and prior standard deviation. So if
okay,
you
just
follow it
substitute
normal,
it.
yeah.
So we can directly apply it in the last formula that we
Yeah,
derived.
you can directly apply with the last formula, I guess. So no need
Okay.
to do this.
Example
So if you are
mean.
okay with this formula,
Yeah, good enough, sir. I will apply it.
so
Thank
from
you, sir.
here you can get what
Yeah, mu naught is
is
there, right? Mu
sigma.
naught is 2. Mu naught
Yeah,
is
mu
2.
naught.
Sorry, mu naught
Would
is 10. Sorry, mu naught is prior, right?
Yeah, what is sigma naught? Prior
2.
standard deviation. So prior is normal 10 square 2 square. Sigma
10,
naught
10.
will be 2.
Yeah, sigma naught is 2 and mu naught is 10, correct? We have
Mu
to use
naught
that.
is 10. What is sigma? Sigma will be 1.
No,
Sigma is
sigma
given.
is 1, 1 already given.
What is n?
1.
5.
N is 5.
N is 5. Yeah. So you have all the values. So you also compute what is x bar.
X bar
So
alone
x
we have
bar,
to compute. Okay, the mean. Okay, of all the 5
x bar
values.
is also, you know, this will be divided by 5 and 5 values are given to you, right? Something like 2.5.
Okay, sir, we'll apply.
Yeah, you add this. You know
Hmm.
all these things. Just put it
Yeah.
here.
Okay.
You will
Now
get
I'm
views.
clear. Okay, I was not clear with that. All those that sigma naught and mu naught. I was confused over there. Okay, so I
Okay,
have
okay.
noted
They are
that.
prior mean and
Right.
prior standard deviation.
Okay, okay.
So if it is given normal, it is prior mean.
Okay, and you're saying if you have something like 1 by root 2 pi, we have to just ignore it because it's a constant.
See, that is just the constant things.
When we are integrating, that's why you're saying that.
Yeah, see, we are just checking. We don't
How?
want the exact value. We are just seeing the proportional thing. So we are worried
Oh,
about the variable terms.
oh.
So if this is proportional to this will obviously proportional to 2 times of this. So you don't need to worry about the constant.
Oh, I was thinking it's something related to integration because earlier also in integration this goes off. So I thought this goes off here also.
No,
Okay.
no, no, no.
Okay,
This
sir.
is
Clear. Now it's clear. Thank you so much.
yeah.
Thank you.
Okay.
There's one
What
more.
about sixth question then?
I think
Okay,
six
you
is
find you tell me what will be sigma naught. The same thing, right?
same thing. Yeah, same thing. Yeah.
Now in this, what will be the sigma naught?
Sigma naught is 1.
Sigma naught is 1. What is mu naught?
Mu naught is 2.
2, right? And what is sigma?
Sigma is root of 2.
Root 2. Yeah, good. That's it. What n is just count the number of samples.
Okay, so that's it. I think you can apply. Same thing. It's the same thing.
Same.
Thank you so much.
Okay then. So it's about 9.2. What is 9.3 question?
Yeah, sir, I only asked that question,
Yeah,
but
yeah.
I cleared that question, sir. I
Clear.
have no doubts in it. Yeah.
Okay, fine. Okay then. In that case, let's move to 9.5. Any other doubts before 9.5? I guess in 9.3 we have done some sort of examples, kind of thing. Right? And in 9.4 also we have taken some problems. And we found frequency tables. So depending on the frequency tables, we estimated the parameter. And last thing is 9.5 model estimators. When we have given you the model, how do we estimate the parameter? Okay. Okay, then in that case, we will move to 9.5. So what is this about? See, this 9.5 is actually given a model to us. We will try to estimate the parameter. So that is why this is called as model estimate. Okay, model estimation. So given a model to us, what we will try to do is we will try to fit that model into some distribution. So depending upon how the model behaves by looking at some samples, we try to predict whether it fits into Poisson or whether it fits into exponential or whether it fits into hypergeometric or geometric or binomial. Okay, so in that case, sir has discussed two problems. One problem is capture recapture. So what this capture recapture means is, so there are some. So let's go with the professor's example only. So there are some animals, some 100 animals you have captured in a forest, and you have tagged them. Like you just put a red mark on some tail or something. So once you are done with that, you left there, and you came back again and randomly taken some 50 animals, and you have observed that only 20 animals are tagged and remaining 30 are untagged. So what we did is first we captured 100 animals. So we captured 100 animals and tagged them. And out of these 50 animals, we have observed that 20 are tagged and 30 are untagged. So this is our data we have with us. So this is the only data we have with us, and we have to estimate the size of the population. So is it there? The guy who has this model distribution. Model distribution. No. Who asked this question actually?
Sir.
You are there, right? Okay. So this is the data we have, and we try to estimate the population size. So how we predict this is, this capture recapture falls under hypergeometric case. Why that falls under hypergeometric case? What is hypergeometric? Distribution. Okay, what is geometric distribution? Not the PDF I want. What is geometric distribution? So when do we apply geometric distribution, or what sort of experiments fall under geometric? Anyone?
Up to first
First,
success.
Yeah. So geometric distribution is we check the first success, right? So this is geometric. So what is hypergeometric? Okay. See, this is exactly like if geometric is like Bernoulli, hypergeometric is like binomial. So here also, uh, what hypergeometric is, some n out of capital N cases, n successes we check. Okay, we are worried about n successes and n minus 1, n minus capital N minus small n failures. So we stop the experiment until n success are achieved. So geometric is about checking only for the first success. Hypergeometric is for n successes. So how long will it take to get n success? So that is what hypergeometric. And what is the PDF of this? PMF of this hypergeometric? What is the probability that
Here is quick question. Both
n takes value k? So some variables, my variables may be different from the professor's variable. No. Is hypergeometric that difficult to understand?
Somewhat.
In the denominator, we should have n, we choose n, capital N choose small n, and in the numerator, we should have two parameters, two parts. One will have the one will have n choose k, and the other one will have n minus capital N minus small n choose small n minus k.
Okay.
Sir, I think hypergeometric, the full details is still not covered properly, like maybe in the upcoming weeks.
Okay.
That's why.
Okay. Then so don't worry then. So hypergeometric, you don't need to worry about it, I guess. So let me give you the what sir variable sir thinks. So what sir has used. Okay. Just a second. Okay. So now this.
Sir, in week 0, professor has covered hypergeometric.
In week 0, is it?
Yes, sir, week 0.
Okay. So what are the variables he has used? Can you just give me?
It's N R
N
R M, small r M.
Small m, is it?
Yes.
Okay. So n is the larger population size, I guess, right?
Yes.
Okay. So out of the population size n, we have taken a random sample r. No? Out of r, what is r?
Yes.
R of type 1.
R of?
Type 1.
Acha, R of type 1, and what is m then?
N minus R of type 2. M is a person
Okay.
from the at random.
Okay. Yeah, got it. So we have population size n. So let us say r male and n minus r female. So this is type 1 and type 2, you can use anything. So out of this r male, if I have seen m successes, okay, I just I just taken m random. I just taken a sample of size m out of this population size. Okay, this is m, right? Even in his case, what is m?
Selected M person informally at random without
Yeah,
replacement.
yeah, selected m persons. Okay, okay, this is what is. See, n is total population. So let us assume total population, and r is, okay, I will use type 1, type 2. So out of this n total population, r people are of from type 1 and n minus r will be type 2. So this is how, and we have chosen randomly m people out of n. So randomly we have chosen some m people. So out of these m people, we have seen some k of type 1 and sorry, m minus k of type 2. Okay, so what we did is, out of the total population, instead of considering that whole population, we have randomly chosen some m people out of this total population, and once I choose this m people, I have found that k people are of type 1 and m minus k people are of type 2. So this is same as this case, capture recapture case. So initially I have tagged some 100 taggings I have done. That means out of my population n, bigger population n, now r denotes my 100. So r come, this r denotes me that animals which are tagged, or it is type 1, and n minus r is type 2 which are untagged. Now there are two types, either the animal is tagged or untagged. Out of this total n, 100 are tagged and n minus 100 are untagged. And later what we did is, we randomly chosen 50 animals out of the total population m. So here m is 50. So even this, see, even here, if I wanted to write the PMF of this, so probability that x takes value k. So that means probability that k of type 1 is observed is equal to r choose k. See, because we have to observe, there are r people are from type 1. Out of those r people, k people should be selected. K people should be there in my random sample m, and the other people should be should come from the n minus r. So this should be n minus r, choose m minus k, divided by, so how many number of ways I can choose m people out of n, and choose m. So this is the number of randomly people. This is the total, what we say, total number of ways m people can be selected out of n people. And what we require is, we require k of type 1 and m minus k of type 2. So number of out of r type 1 people, choosing k of type 1 people is, I can choose r choose k many times ways. Sorry, r choose k ways. There are r choose k ways I can choose k people of type 1 out of r people of type 1. Similarly, out of n minus r type 2 people, I have to choose m minus k k out of them. I can choose in n minus r, choose m minus k ways. So this is the event probability total number of ways. Yeah, this is the probability that x takes value k. So this is related to hypergeometric thing. So even here you just have to identify what is r, what is n, what is m in this case. So in this case, n is the total population which we need to predict. So n is unknown, and what we know is r we know. So we have tagged 100 animals and we tagged them. So r is 100 here, and we know m. We have chosen 50 animals out of it, and we know k, small k. See, k is this 20 are tagged. 20 are tagged is 20 are type 1. So k we know 20. So once you know all this things, we are ready to predict capital N. And also you see, you don't need to worry about what I said till now, but you need to worry about this thing. So if we have a hypergeometric thing, if my random variable follows hypergeometric distribution, I need to worry about what is the expected value of that hypergeometric distribution. So expected value or mean of this hypergeometric distribution will be, so m into k divided by, so m into r divided by n. Okay, you just have to worry about this thing. So expected value of x, where x follows hypergeometric distribution, expected value of x is m times r divided by n. So what is this expected value? So you have one sample with you. You have only one sample. I just captured only once, and out of these 50 animals, I have observed 20 animals are tagged and 30 animals are untagged. Okay, if the animal is tagged, you give the value as 1. If the animal is untagged, you give 0 to it. So out of 50 animals, I have observed 20. So what is the expected value or mean of this thing?
20 by 50, right?
20
by 50.
50 into 100 by,
yeah, that is 50 into 100 by. So I'm not asking what will be the expected value. So what is the sample mean?
20.
See, I know m, I know r, I don't know n, but I know expected value of x. So what this will be? So what is
20.
how is my second question.
We are given only one sample.
Yeah,
X.
we are given only one sample. What is the sample mean tells me. What is this x actually? Or what are we trying to find? What are we trying to find? What is the random variable which follows hypergeometric here? This thing. Okay, this thing taking value k. So we are worried about this random variable. So that means we are worried about the type 1. That means type 1 denotes the tag thing. So we are worrying about the number of animals that are tagged. And the number of animals that are tagged is a random variable. And that random variable follows hypergeometry. So that means we are worried about
R.
R. Correct. R. Are we worried about R? See, R is fixed, right? In this, initially I have tagged 100. My R is 100. R is not a random variable. What else is a random variable? This
During
particular,
recapture,
yeah, this
we were
particular
tagged.
20 is a random variable, you see. See, once if I choose 50 animals randomly, not every time you will get 20 tagged animals, right? You may get 0 at some point, you may get 1 at some point, you may get 20 at some point, you may get 19 at other point, other samples, I mean. So in this case, I just taken only one sample out, which are 50 animals, and out of that samples, I got 20 tagged animals. Okay, my M or my this particular K takes value 20 in this particular sample, right? So this particular K is 20 in sample 1. So if I have considered sample 2 and I have randomly chosen, again I mix this 50 animals, again I have chosen randomly some 50 animals, but this time I have observed only 15 tagged, and rest of the 35 are untagged. Okay, sample 1 we have observed 20 tagged and untagged, and sample 2 I observed 15 tagged and 35 untagged, and I have considered again a sample 3. In this case, now it has 18 tagged and 32 untagged. So if I have considered some more than one samples, now you see the number of tagged animals differs. So this is my x1, this is my x2, this is my x3, like this. So if I have considered different samples, I might have got different number of tagged animals each time. So I am worried about how many number of tagged animals are there. This number of tagged animals follows hypergeometric is the observation. So this particular thing follows hypergeometric. As I have observed only one particular sample, what is the mean of this sample? So I have only one sample, and out of that x1 is 20 and I have observed only one time. So what is the expectation of x here?
20 by 50, right?
20 by 50.
20.
20 itself. See, x1, x2, x3 and so on xn are, see, this x1 denotes the number of tagged animals for the first sample. X2 denotes number of tagged animals for the second sample. Likewise, xn denotes, if I keep on doing taking the samples again and again and again and again, I will get different values and I am noting down it like this. But I have taken now in this case I have taken only once. I have just taken only one sample. There is no x2, x3, x4 and so on and everything. I have only x1 with me, and this x1 is 20 and the expected value of x1 is 20. So I have only one value to my random variable, and what is the expected value of that particular random variable? If I have only one value, it is the same thing, same value, right? Same value, right? Am I making you confused? Or... Okay, look it in a simpler way. Just identify which random variable you are looking into. So our random variable here is the number of tagged animals. So the number of tagged animals has taken only one value, which is 20 in one sample. So my random variable taken value 20, and I don't have my random variable value takes 20 value. So if I wanted to find the expected value of that, expected value is sample mean. I have mean, right? So expected value of x will be x1 by 1. So I have only one sample with me, and out of that I have only value 20 by 1. So if I had taken 3 samples like this, then it should be like x1 plus x2 plus x3 by 3. So this will turn out to be 20 plus 15 plus 18 by 3. Now the expected value may be this, it will turn out to be this. So firstly I observed 20, second I observed 15, and third I observed 18. So what is the expected number of tagged animals I see will be sum of all the three times we have sum of 3 values divided by 3 is the, which will be the sample mean. So that is why expected value of x will be 20 here. Okay. See, the reason is because only we consider one sample, and out of this one sample we have only one value. Expected value of one value is the same value. So once you know this is 20, you take it equal to the 20, and 20 will, we know the other values. This is 50 and this is r is 100 divided by n. So from here you will get the value of. So even this is also the estimation. This is not the exact value of n. This is just we estimated that this will be equal to some 250. Okay. Okay. Let me check. Have you understood or not? Okay. In that question itself, I'm increasing my samples now. Now, firstly, we have tagged 100 taggings are done. 100 animals are tagged. And for the first recapture, I recaptured 50 animals. And out of these 50 animals, 20 are tagged and 30 are untagged. Okay. This is first recapture. And in the second time, second 50 animals are observed. And now, okay, 15 are tagged. 50 animals. This time I observed 30 are tagged, 20 are untagged. Am I audible? Hello?
Yes, sir.
Yes, yes.
So in the fourth time, I observed something like again 20 and 30 are untagged. And in the final time, I observed 10 and 40 untagged. Okay, I have now my experiment, I have done 50 times I recaptured, and now my question is, so what is the population size now? Estimate the population size. So you should get a better estimation now. So initially we have seen only once, but now we are taking it, taking 5 samples. So we are recapturing 5 times, and we are observing the number of tagged and untagged thing. Now just do it for a second. So now estimate the population size. Now we need a better estimation. We should get a better estimate.
263.
263. And the thing is, this M and R won't change. M and R are fixed. So what is m? We are actually, this m is 50. So every time we are observing only 50. And r is 100. So we tagged only 100 in the initial. So m and r are fixed. Now what varies is the expected value. So estimate. So one of you guys said 263.
Yeah, it's 263. Expected value is 19.
Value? Expected
Expected
value is
value is coming
19.
at 19.
Okay.
Sample mean is complete 19.
Okay. Yeah. Now this time, what changes is this expected value. So this expected value of the number of animals we that are tagged. So what is that expected value is? So we have seen 20, 15, 30, 20 and 10. So 20, 15, 30, 20 and 10 divided by 5. So this will be the mean of number of animals that we observe that are tagged. So once we find this, we get 50 plus 20, 70, 80, 95 by 5, which is 19. Now what we have to do is simply we know that as axis follows hypergeometric, expected value of x will be m times r by capital N. So n will be 50 times 100 by 90. So it should be slightly more than 50 times 100 by 20. So if you compute this, I guess this is approximately 263. So like this. So depending upon the question, you should identify or you should estimate the parameter, or you should estimate the variable which we are asking. Okay, this is about.
Sir, in lecture, professor has that formula m into r by n. So that's complete.
See, that is what see, the expected value of hypergeometric thing will be m into r by n. Do I have to prove that or
Proof, sir.
prove? Okay. So we know, just now we have seen probability that x takes value x, let's say, and we have parameters n, r and m. So what is the probability that x takes x? So that means x success we need. So that means r choose x times n minus r choose, and this will be m minus x divided by n choose m. So this is the probability that x is equals to x, and now we know expected value of x is summation x is equals to from 0 to, okay, what is the range of x here? What will be the range of x? Tell me that. So it starts from 0. So till where this will go? Will it go to till n or till r or till m? Am I audible?
Yes, sir.
Yes, right. Okay, you are thinking. Okay, what is the range of x? What will be the range of x? Okay, for simplicity, let us consider R is greater than M.
Is it R, right? Range.
Will it be R or
M,
I
M.
said R is greater than M. Consider this uh, uh, assumption. It's an assumption. Assume R is greater than M. Now tell me till where my X goes. Will it goes to M, R or N, capital M?
M.
M. Correct. See, you can see here, right? See, M minus X should be greater than 0 or equal to 0. And X should be greater than or equal to 0. Right? From this, you can say, you can get X should be, X is less than or equal to M. Why this is because, see, M is actually, we are choosing M people out of N people. And what is this X? X is actually the number of people that belong to type 1. So you are choosing only M people. Can your X take values greater than M? So you are choosing only 100 people, let's say 100 people. So you are choosing 100 people out of your population, bigger population. Can your X go beyond 100? So can your X, can we observe type 1 people more than 100 in 100 sample?
No.
No, right? So that is why your X, see, first and foremost thing when you compute expectations or whatever, you need the distribution and you need the range of X, you need the PMF of X. So once you get all those things, then you can compute the expected value. So now here X starts from 0 and it goes till M. And expected value summation X times PM of X. PMF will be probability that X is equal to X. Now this is summation X is equal to 0 M X times R choose X and minus R M minus X divided by N choose M. Okay. Okay. Now you can see this, I can write it as R factorial by R minus X factorial divided by X factorial into whole divided by N minus M factorial into M factorial. So this is summation over X is equal to 0 to M. So what we do is we just cancel out this you just rearrange the things. The numerator. So what I do is I will write the factors R times R minus 1 factorial divided by R minus X factorial times, I will keep this as it is, N minus R factorial divided by N minus R M minus X factorial divided by, now you see I will write this n factorial as n into n minus m factorial. I will write this m factorial as m times m minus 1 factorial. Why I am writing this is you will get to know in a minute. This will be summation till yeah. Now you see I can bring this r outside, this m outside, this m goes to the numerator, this n outside. So this will become rm by n summation x is equals to 0 to m. This r minus 1 factorial divided by r minus x factorial into x minus 1 factorial is nothing but r minus 1 choose x minus 1. So you can verify this. This will be r minus 1 choose x minus 1 will turn out to be r minus 1 factorial by r minus x factorial into x minus 1 factorial. And this is same as n minus r m minus x. Now the numerator will become n minus 1 choose m minus 1. Okay, if you observe deeply, this is an hypergeometric probability. This is nothing but probability that x takes x minus 1. Correct. Okay. Okay, what we will do is, when x is equals to 0, this will be 0, right? Product. So when x is 0, this will be 0, right? 0 times this. Am I still in the call? Hello?
Yes, sir.
Yeah. So the first term will be 0 because there is a product with x, and when x takes 0, this will be 0. What I would like to do is, I would like to remove 0 there. I can replace it with 1. So this replacing with 1. Here I will get 1. Here I will get 1. So this is nothing but this is yeah, this is okay. So if you see here, this is rm by n multiplied by probability that x takes 0 plus probability that x takes 2, probability x takes 1, x takes 2, x takes 3, and so on, probability that x takes m minus 1. So if you add up all these probabilities, we should get 1, right? So if you see here, so probability that x takes 0 has some value, probability of x takes 1 has some value, probability of x takes 2 has some value. Likewise, probability that x takes m minus 1 will have some value. What is the probability that x takes m? That will be 0, 1, sometimes r of r chosen. Okay. Yeah. So this will turn out to be you just have to add all the probabilities in the support of x. So if you add all the probabilities in the support of x, this will turn out to be equal to 1. And ultimately we will get rm by n. Okay. But yeah, doing all this, I would state that again, you don't need to worry about the derivations of expected values. Also, you no need to remember the expected values. We will give you the table, but it's just for your understanding purpose. Okay. Am I audible?
Yes, yes.
Yeah. So, any other doubts?
Venkatesh Apul here.
Mm-hmm.
So, I would just like to understand. I mean, while you were explaining, I also was looking at the questions where I had asked the doubt initially.
Mm-hmm.
Would it be possible just to give some more um, process-related knowledge on this normalization bit, where we should be using that normalization and how to reach across? I'm getting a bit confused looking at the question, so want to use this opportunity if we can discuss a little more around normalization.
Okay. Just give me some 2 minutes. Okay.
Yeah, yeah,
Let me ask
sure.
other guys to.
Yes, of
Are there
course.
any doubts in week 9 particularly? Anyone? No?
But I'm yet to see the remaining videos, so I don't have any doubts as of now.
Okay. So please do watch, and tomorrow also I guess there is a session on week.
Yeah. Tomorrow I will definitely watch for the graded assignment. That only helps me.
Yeah. So please do watch it, and syllabus for quiz 2 is till week 8 only.
Yeah, but I think we are adding up all the best of, I think, 7 or 8 graded assignment marks for the final score. So we have to concentrate on the graded assignments also.
Yeah, graded assignment of 9 too. But what am I saying is syllabus will be more emphasis on weeks 5 to 8. When I say more emphasizing means it's like it will be around more than 90%. Definitely more than 90.
So this
And each
Bayesian
want to
estimation will not be covered for this syllabus, right?
no. This Bayesian estimators, and later we will see the
Okay.
distributions
Till
of
maximum
hypothesis.
likely till maximum likelihood we have to.
Yes. So till
Okay. So
maximum likelihood, and the paper is also bit easy. Uh,
okay.
Don't go in deep preparation. Just make sure your basics are good. So make sure a given sample to you, if you are able to come up to find the likelihood and later derive it or do the R max of
Okay.
it.
Okay.
Yeah. So if you are able to do that is good enough.
Okay. Thank you. Similarly, like the last quiz one, the formula sheet will be provided, or how it is planned?
It is. It will be
Okay.
provided.
Okay. Thank you.
I think this time they will also provide all the FC values, -3, -2, stuff.
What is that? What is
That
MC value?
FZ, F of Z.
Yeah. That is definitely. I guess it is
In one graded
directly
assignment
given in the hints itself.
question, and in
Yeah,
one
in the
graded
question itself.
assignment, it was not there last time. I took it from the tutorial.
Oh.
Yeah, one was missing. It's okay.
Okay. See, these type of things we never give you. So what is the if x is normal 0 1? So what is the probability that x takes less than or equals to?
Point 0.5.
Yeah. So it is 0.5. So there is no need of, what we think is there is no need of giving the value for this.
Yeah, but it was not for this value. It's not.
Okay, it was not for this
Yeah.
value. Okay. But this is a straightforward thing. You should actually remember. Don't expect us to give this thing also. So half of the area of this graph will lie below left side of 0 and half will lie to the right side of 0. Probability that x takes lesser than 0 values is half, and vice versa. This is equals to this thing also. Okay. For other values, for at least for quiz we will definitely give. You don't need to buy heart anything. Okay. Yeah. So this is about quiz 2. Yeah. Consider this more emphasis on 5 to 8.
Any idea on the number
Estimated, we
of
try to estimate it.
questions? Any idea on the number of questions, and would we have that step questions also? Writing down the steps for the questions, or
Right.
will that not be there?
It will be there. It will be there for few questions as like in quiz 1.
Okay.
Yeah. So yeah, that is. I hope you guys know what that is for. If you have given the correct answer, that will not impact. If you have gone wrong only, then this will be taken into consideration.
And again, in the same way, right? I mean,
yeah, in the same way.
So if it is required to answer three steps only, though there might be 5 or 6 steps, but if we write 3 steps out of any of those 5, 6, we will be eligible to get the complete marks for that question. I mean,
Yeah.
whatever are these marks for the step question, we will get that, right? Even if we mention
Right.
3, as
Right.
per the question asked. Okay.
As per the question, you should enter. Yeah.
Because in quiz 1, there was ambiguity. 2 questions were asked together, and we had to write
Okay.
the steps.
Okay.
And till date, at least I don't know what is the mark that I have got for that question, whether I have got the complete mark, yes or no.
Okay. So see, the thing is, there is no partial markings for that thing. Is it there, or I don't think it is there. So either you will get 1 mark or you won't get mark. So if you have given the correct answer, then you will get the 1 mark.
Any idea on the number of questions that we are expecting? I mean, though it does
Number of
not help,
questions.
but just
Yeah. This time there are only few questions, not like this one. So including subparts, it might reach 14. It might reach 14, not more than 14, including subparts. This is okay. Maybe in the revision session, we will provide you with exact percentages from each thing, and also the number of questions. So once you have a clear idea how the paper going to. Okay. Okay. Fine then. So those who are done, you can leave this session. Yeah. Have a good day.
Have only one doubt. In the final lectures of week 9, usually we estimate the parameters, the expected value like that. Suddenly in the final lecture, we are going for error. I don't know why we go for error. Or can you just say the steps, whatever we want to do for the fitting the estimations? What all should we calculate?
9.4, I presume.
Yeah, 9.4.
Oh.
Because
so till 9.3.
Yeah, it is tough, but this part is very confusing usually.
Okay. So why we are going for error is See, that is what even.
No, in the previous things, we just calculate by method of moments or ML, right? We find the parameters. Here, why do we bring error? I'm just not understanding.
Okay. So
I think that is for normalizing. I think that's what sir told. So that is a bit confusing.
okay. So regarding this, can you just go back to the previous live session, last live session? So even
Okay.
Nikita explained this thing
Okay. Okay. Yeah.
clearly.
Yeah.
Okay. Just go back, watch that.
Okay.
Yeah, I think it should suffice here. Okay. Any other things? No. Okay then. Shall I go back to week 7 then? Okay. Is Apple here?
Yes, Venkatesh, I'm here.
Yeah. Okay.
You want me to say specifically the questions and then ask, or do you want to take it separately? I mean, whatever is you think appropriate.
Either way works for me. You can give me the question and we can discuss on the question and it will give you better idea, I
Yes,
guess.
exactly, right. So, question number from practice assignment, question number 10, question number 11, and question number 13. So in all the three questions, we are using the CLT, but the approach is different.
Okay. See, question number 10 is a company sells eggs whose weights are normally distributed
Right.
between
So over here, where I'm
70.
stuck is in one of the step, it says this x bar minus 70 is the normal distribution with mean 0 and variance 1. And then this x bar minus 70 is considered as z itself, but there is no normalization that has happened for x bar minus 70. When I say normalization, over here sigmas, there is no division by sigma square by root n in this step, and it is considered itself as normal. So why x bar minus 70 is considered as z?
Okay, let me see this. So it is given normally distributed with mean 70 and standard deviation of 2 grams. Suppose that these eggs are sold in packages that each contain 4 eggs. Assume that the weight of each egg is independent. What is the probability that mean weight of the 4 eggs in a package is greater than 68.5? Right. Right. Okay. So we have been given, so x is a random variable which is weight of each egg, right? And this particular egg follows normal. What is mu is 70, so 70 comma 2 square. So it is given to us. What we
Yeah,
are
2
asking
square.
is, so probability that the mean is greater than or equal to 67.5.
68.5.
8.5. So
Yeah.
it is greater than, greater than.
Yeah, yeah.
What is it?
68.5 greater
Is
than.
greater than 68.5. So we know x bar is x1 plus x2 x2 plus x3 plus x4 by 4. So we are considering 4x and sample mean will be x. Okay. So let me consider S as x1 plus x2 plus x3 plus x4. So we start from basic.
Yeah, please. Yes, thank you.
So we know when we have x1, so this is how CLT works. If you have x1, x2 and xn following some distribution IIDX, so it is following some distribution, we don't know what distribution is. What CLT does is, whatever the distribution may be, this particular thing S, which is the sum of the random variables, when you consider this particular thing as S minus n times mu divided by sigma root n follows normal 0 1. I'll tell you what mu and sigma is. So this mu and sigma are, so when I consider this particular thing as normal, normal with mu and sigma, standard deviation sigma. Okay, so when x follows, when x has expected value of x is mu and the variance of x is sigma square. So you have a distribution, some distribution, and you know the expected value of the distribution is mu, and you know the variance of that particular distribution is sigma square. You know this, and you have n samples with you. You consider this as, which is the sum of all the samples, sum of all the x1, x2, xn. Now what CLT tells you is S minus n times mu divided by sigma root n follows normal 0 1. Okay.
Yeah.
Correct? Yeah.
Yeah.
So now let's come back. So we have been asked to find this thing, right? But we know when we know this thing, S minus n times mu by root sigma root n follows normal 0 1. So what is S here? X1 plus x, what is x s here? X1 plus x2 plus x3 plus 4 x4.
Venkatesh, over here, where you have written S is equal to x1 to xn, we just have 4, right? So we will consider x1 plus x2 just 4 values, right?
Yeah, there's 4 values. This is general case.
General, okay. Okay, fine, fine.
So now in our case,
yeah,
n is 4 only.
4 only, correct,
Okay.
right.
Now our here in this case, S will be x1 plus x2 plus x3 plus x4.
And this is, you have written capital X, right? These are capital X's.
Yeah, these are capital X.
Yeah, okay, fine.
Now you see our x bar will be, if I wanted to write in terms of S, our x bar will be S by 4. So this numerator is nothing but S. Right? Now what I have to find? Probability that I just replace x bar with S by 4 greater than 68.5. Okay. Now this is equal to this.
And can you also tell why we are doing this? I mean, I understood S can be written as X bar can be written as S by 4 and then we do that. But what is the thought to take this approach in order to calculate?
See, because we know only the how to convert this sum of random variables to normal. So when you know this x1 plus x2 plus x2 till xn as S, then that S minus n times mu by sigma root n follows normal 0.
Okay, so we have to bring the existing distribution to this n01.
Yeah. So in terms of this distribute, in terms of this random variable x1 plus x2 plus, this is also a random variable S.
Yeah.
This is also a random variable, right?
Yes, right.
These are all random variables. This is sum of n random variables, which is also a random variable. But once you know this random variable S, then the S minus n times mu by sigma root n follows normal 0 1 is what CLT
Hmm.
tells us. So that
Okay.
is why we convert that into
Yeah. Okay.
S in terms of S.
Fine.
So once you convert that, we will get something like probability that S greater than 68.5 times 4. Just multiply 4 on both sides. So this we will get. Okay.
Hmm.
Now we have S with us, but we have to subtract minus n times mu by sigma root n in order
Hmm.
to convert, in order to get, let us say this is Z, which is standard normal variable. So what I have to do is, this is equal to probability that S minus, I know n, which is 4, right? In our case, now in our case, we have 4, n as 4. What is mu? What is sigma? It is given in the question.
Yeah. 70.
So mu is given as 70, sigma is given as 2.
Yeah.
So I just have to subtract S minus 4 times 70 divided by 2 times root 4. So the same operations should be done to this also. So 68.5 times 4 minus 4 times 70 divided by 2 times 2. So now this particular thing is it, right? This is S minus n
Yes.
times mu by 2
Correct.
times
Right.
root n.
Yeah.
So first and foremost thing is, whatever the question is asking about, question here the question is about x bar. So probability that x bar takes greater than 68.5. So if you don't know how to convert x bar to standard normal, just convert this x bar to S and then S to standard normal. So we know how to convert this S to standard normal Z, and whatever the random variable here given to you, just convert this into in terms of S. So once you can do that, later it's just conversions. So this
Yeah.
x bar random variable converted to S random variable. Now this S converted to some, with some operation converted to standard norm.
So
Is what it is.
the second part will come to minus 1.5, right?
That if we calculate, we will get to know. So this is 4 times of minus 1.5 divided by 2 times of 2. Yeah. So probability that Z is greater than minus 1.5.
Okay. Yeah. This makes clear.
Okay.
Fine. Okay.
So you use that table or the value is given to you. This is nothing but 1 minus of Fz minus 1.5, right? This is 1 minus of probability that Z is less than or equals to minus 1.5. And this is nothing but Fz of minus 1.5. And this, if you know the value of this, just substitute it and subtract it from 1. Okay.
Yes. So this approach is still understandable because in the solution that has been provided, it's doing x bar minus 70 and then taking directly to Z.
Okay. So x bar minus 70 is standard normal 0 1.
Yes, right.
Okay.
And then that has been considered as this Z and
Okay.
equated forward.
Okay. X bar minus mu is standard. Achha. This is 0 1, is it? What is this x
Yes,
minus?
correct. X bar minus 70. Yeah, and that is what is provided as a solution.
Okay, let me just open that. Are we doing wrong? Okay. Okay. So this is a normal distribution, but maybe, right. Yeah. So this is also a good approach, but this requires some level of understanding of normals and everything. So whatever I discussed is a standard approach to any question.
Yeah, got it. So that
But
is what we can follow in all the questions.
yeah, all the questions you can follow that thing. So whatever the random variable is asking, just convert it into S, and later you can convert the test to standard normal.
So I guess the same approach has been taken in question number 11 also.
So question number 11 is Poisson. Question number 11 is X bar. X bar. Whatever I discussed. Question number 11 is that case, right? False in
Right.
that case.
So I mean, for 10 also it is applicable. For 11 also this can be applicable.
Yeah.
And I guess for 13 also this becomes applicable then.
Yes, even 13 you can do the same way. 13 is just the fair dice roll 3600 times and 630. Yeah.
Yeah. Okay.
Fairly.
Fine. Fine,
You can
Venkatesh.
use the same. But what differs in question 10, the approach is they just computed, the sum of normals is normal, right? They use that property.
Yeah.
So x bar is basically the sum of normals. That is 1 by 4 times x1 plus 1 by 4 times x2. Linear combination of normals. x3 plus 1 by 4 times of x4. Okay, so from if it is linear combination of normal, we know that x bar is also a normal. Combination of normals is a normal again. So this will be x bar will be normal with mu and sigma square, where mu is this thing. Mu is the expected value of x1, x1 or x2 or x3. So mu will be equal to the expected value of x1, but sigma square will be equal to sigma naught square by n.
Yeah.
Okay. Yeah. So from here they will get expected value of x bar as 70. Expected variance of x bar as so sigma naught square is 2 square by 4. They will get 1. So what we will get is x bar is normal 70 with standard deviation 1. So that means it will be like this. Somewhere it will be like this, and this value is 70, and standard deviation is 1. So in order to convert this x bar, which is normal 70 comma 1, we just shift this distribution to 0. We will bring it to 0 like this.
By
So this
subtracting
is
70.
0. Yeah, by subtracting 70, we will shift this graph 70 units to the left side, and it will become the standard normal distribution. So if this is this, x bar minus 70 will be normal 0. That is what they say. See, that is because the given random variables are normal, you can use this process. But if it is not normal, you have to again do CLT. The way I did, you have to do it in that way. So whatever the distribution is, you can use that approach, what I said. So whether it is normal or Poisson or whatever the distribution may be, you can use that approach. Okay? That is a standard approach, and these are some shortcuts. Whenever normal is given to us, you can directly do this instead of going to S and coming from there. Okay. Yeah.
Okay.
That's it, I guess. So 11th is also the same thing. 13th is you can use the same thing.
All these are which week? Is it from 7 activity?
Yeah, these are from week 7 practice assignment.
Oh, nice.
Okay. So in that case, yeah, we are running to even the time is up. Okay then, so thanks for joining and have a good day.
Thank you, Venkatesh.
Thank you.
We'll meet in the next session.
Thank you.